These 4 astronauts are the crew of Artemis II. Their objective is to fly this Orion spacecraft beyond low Earth orbit and carry humans back to the moon for the first time in over 50 years. To the casual observer, the trip looks like a straight shot. You simply point the nose of the rocket at the moon and fly directly toward it. But as this simulation demonstrates, going straight up doesn't work. Once the engines stop firing, gravity pulls the vehicle back toward the ground. Reaching deep space requires a different approach. You cannot fight gravity by flying away from it. You have to use gravity to your advantage. Entering orbit requires turning the spacecraft sideways and accelerating to approximately 28,000 kilometers per hour. This diagram shows the result. The spacecraft is actually falling toward the Earth, but it is moving sideways so fast that it constantly misses the surface and curves around the planet. This sideways momentum locks the ship into a continuous loop. Once you are in this loop, your terrestrial intuition no longer applies. Simply pointing the ship at a new destination and firing the engines will not move you in a straight line toward it. In reality, orbits are rarely perfect circles. They are usually stretched into a geometric shape called an ellipse. The periapsis is the lowest spot, closest to Earth. On the opposite side is the apoapsis, the point of maximum distance. To travel deeper into the solar system, the crew must find a way to intentionally move these 2 points further away from Earth. Navigating space is about reshaping this geometry. To change your destination, you have to change the shape of the ellipse itself. The way you change an orbit is counterintuitive. If you want to raise your highest point, you do not fire your engines when you are at that high point. Instead, the crew waits until they reach their lowest point, the periapsis, and fires their engines in the direction they are already traveling. Adding energy at the bottom of the loop physically pushes the top of the orbit further out into space. This maneuver is a Hohmann Transfer, a fuel-efficient method for changing altitudes using 2 specific burns. First, the ship fires to stretch its orbit into an ellipse. After coasting to the new high point, a second burn circularizes the path at that higher altitude. Orbital mechanics is a game of deferred results. Energy you spend on one side of the planet only changes your position on the opposite side. We can see this logic in the flight plan for Artemis II. After launch, the Orion spacecraft first establishes a stable low Earth orbit. Once in place, the crew will perform an engine burn at their lowest point, specifically designed to stretch their highest point thousands of miles away from the surface. This creates a highly elliptical Earth orbit. This phase acts as a 24-hour safety check. The crew can test their life support systems, while the shape of the orbit ensures they will naturally swing back close to Earth for an easy return if any issues are detected. After the systems are cleared, the crew coasts back down toward the Earth for their final approach. At their lowest and fastest point, they execute the translunar injection. This engine firing provides the final burst of velocity needed to break away from Earth's immediate vicinity. This maneuver stretches the opposite side of the ellipse hundreds of thousands of miles into the blackness, placing the spacecraft on a path that directly intercepts the moon. Reaching the moon isn't about flying in a straight line. It is about understanding the geometry of gravity and using the mechanics of the ellipse to turn a fall into a journey.